So to verify the performance of a transmission line or to evaluate the performance of the transmission line, first we have to model the transmission system. So transmission system depends upon the length of the conductor. So electrical length of the conductor, that is classified into three categories. One is one is short transmission lines. Second one is medium transmission lines. Third one is long transmission lines. So since the operating frequency is at 50 hertz in our system, so if we calculate the frequency multiplied with length, which is equal to 4000, it is a standard value. So frequency, if it is 50 hertz, the length of the conductor or the transmission line comes around 80 kilometers. If the length of the transmission line is less than 80 kilometers, the system is said to be a short transmission line. If the length is in between 80 to 160, it is termed as medium transmission line. If it is greater than 160, so it is termed as long transmission line. That's what we have seen in the earlier classes. Performance of the transmission line. So introduction, the main objective, and how the performance can be evaluated based on efficiency and regulation. So the next step is finding efficiency. Efficiency is nothing but power delivered at the receiving end by power delivered at the receiving end plus losses. You will get efficiency. So regulation is nothing but it is no load minus full load value by full load into 100, the mathematical expression. Otherwise, the change in voltage at the load terminals from no load to full load, so divided by full load value, you will get regulation. So this is what we have seen in the last class. So representation, the parameters, series elements in a transmission line. So to evaluate the performance of the system, first we have to calculate the constants, line constants. Those are series line constants, series resistance, inductance. Similarly, shunt capacitance and conductance. These two are shunt elements. These two are series elements. Resistance and all these are distributed parameters. So, and if we observe the voltage waveform or current waveform on a transmission line, it travels with a speed of light speed. So it comes around 3 to 10 to the power of 8 meters per second. So velocity of a light. So similarly, which is equal to the velocity of a voltage or current waveform on a transmission line. So that comes around, the wavelength comes around 6,000 kilometers. It means that, so after 6,000 kilometers, you will get the same value. So whatever may be the value at this location, so if we calculate the instantaneous quantity either for voltage or current waveform, so after 6,000 kilometers, you will get the same instantaneous quantity. Okay, so that is based on this waveform. So voltage distribution. So here, if we consider for a 160 kilometers up to 160 kilometers, in some textbooks that may be around 200 kilometers. So up to that point, the voltage or current variations are same, whether if we use distributed parameters or lumped parameters. So if we use lumped parameters, the calculations will be easy. So there is no much difference in case of performance calculations. That means efficiency and regulation. That's why we go for lumped parameters while representing a short transmission line or a long transmission. So long or short transmission line, sorry, not long, medium or short transmission line up to 160 kilometers. the voltage variation or current variation, it is almost same. So that's why we can go for a lumped parameter instead of distributed parameters. Okay, now, so this is the classification for the short transmission line 80 kilometers, and voltage varies up to 20 kV. If it is less than 20 kV, that is termed as short. In case of medium, that is 80 to 160, and the voltage level is in between 20 to 100 kV. Okay, so here we have to consider, in case of short transmission line, we neglect the shunt capacitance. Shunt capacitance more, it depends upon the length of the conductor and also the operating voltage. So for a short transmission line, we can neglect the shunt elements, only the series elements are there. Simply if we calculate either performance of a regulation or efficiency, so if we consider the shunt values, or if we just eliminate the shunt values, so you'll get the same, almost the same values. That's why you can simply neglect the shunt elements. So, and we using just resistance and inductance, we can evaluate the performance of the short transmission. Whereas coming to medium transmission lines, so medium transmission lines of length between 80 kilometers to 160 kilometers, and also the voltage ranges from 20 to 100 kV. Here the voltage value is little bit high. Similarly, if we calculate the capacitance and also the charging currents a little bit more, we can consider. So in terms of total values, so here we have to consider the shunt elements, so shunt capacitance. So we cannot neglect. If we neglect the shunt elements, the practical values and the theoretical values may not be coincide. So that's why we have to consider the shunt elements. So while going, instead of going distributed, we can use lumped parameters in medium transmission line. And also we can consider this shunt capacitance at the center, or we can distribute we can split into two capacitances. One is at the sending end, other one is at the receiving end. If we consider the shunt capacitance as a lumped value at the midpoint of the line, so that is termed as nominal T model. If the same shunt capacitance is half is connected at the receiving end, and half of the value, if we assume it as a at the sending end, so that is termed as, that model is termed as nominal pi model. So in case of medium transmission line, we can use either nominal T model or nominal pi model to get the efficiency and regulation of a medium transmission line, or performance evaluation of a medium transmission line. Whereas in case of long transmission line, that is which is greater than 160 kilometers and greater than 100 kV, the parameters we have to use distributed models only. So here if we take lumped parameters, the practical values and the theoretical values may not be coincide. That's why we have to go for distributed parameters. So once we use the distributed parameters and the model up to 250 kilometers, we can use nominal pi representation. So here if we calculate the performance of this long transmission line, that may be you will get the same values. So if we use distributed parameters, so rigorous methods we have to use. So let us consider, let us evaluate, or let us model when we use the long transmission lines. Now this is representation of a transmission system. In transmission system, there are generators, loads, and transmission lines. So we can consider all the three transmission lines as a single transmission line, and also the total load can be considered as a single load, total generation can be considered as a single generator. So if we represent in this fashion, that becomes a single line diagram. So single line diagram is very much important in case of power systems. Okay, power system analysis, we use the same type of representations. Okay, this we have to remember. Even though if we represent in this fashion, this is single phase representation of a three phase balanced system. Here it is. So that three phases is, instead of writing three phases, simply we have represented with a single phase. Instead of representing three transmission line, we have used only one transmission line. Instead of using three phase loads, only one phase we have connected, and this is a single phase representation of a three phase load. This is a three phase system, but to reduce the complexity, so we have reduced the number of phases. So this is a complex three-phase system, a three-phase diagram. All the three phases in the generator, so all the three phases at the load and three transmission line. This entire things can be represented using either single line diagram, or we can represent using a single phase, a representation of a three-phase system. Okay, next. So generally we neglect the transposition, so it may not affect the values, so that's why we neglect. Now coming to short transmission line. So now our aim is to evaluate the performance of the transmission line. Means how a short transmission line can be represented, the first step. Next, second step, we have to find out the efficiency and also the regulation of a short transmission. Okay, so once we get in the first chapter, once we evaluate the resistance, inductance, capacitance values for a given transmission line, the next step is whether the system, how it performs. That means how the efficiency is going to be. So how the regulation is going to be. So once we know these values, so we can find out the performance of the given transmission. So here the representation. For a short transmission line, we have neglected the shunt elements. So only the resistance and inductance are there. Simply the entire system, a three-phase system, can be represented by a single phase representation of three-phase system. This is here it is single phase resistance, the entire resistance. It is also represented in using lumped parameters, resistance value and also reactance value. So the shunt elements are just neglected. Here VR represents the, what is VR? Receiving end voltage. Similarly, Vs is sending end voltage, Is is sending end current, where IR is receiving end current. Now, using phasor diagram or vector diagram, we can find out the regulation. So formula for regulation. This is representation of a short transmission line, simple short transmission line. Okay. So for a very long transmission line, we can also neglect. In some cases, we can neglect. For a complex network, the resistance can also be neglected. So now, based on these are the series element. If I assume this is a voltage source, here it is load is connected. So voltage across the load is VR receiving end voltage. So in between the source to load, there's a transmission line is there whose value is R plus JX impedance value. Now everything is connected in series. In series elements, we can assume the current can be taken as a reference. So here in this case, I have assumed IR as reference. So the reference current is IR. So if we assume again, most of the loads are inductive loads. So in case of inductance, current lag behind voltage by an angle theta. So here it is. Current value always, it is behind voltage. If we take voltage as reference, okay, so current always, so it is some more lagging behind voltage. So these two are receiving end voltage and receiving end currents. Okay, now if I take the voltage drop at the resistance, current passing through the resistance is in phase with this current. Okay, So similarly, voltage drop is also, since it is voltage and current are in phase in case of pure resistance. So voltage and current are in phase with this IR. So I have represented this drop IR into R or I into R drop can be is in phase with resistance. Okay, this is the drop, IR drop. Now, in case of inductance, pure inductance, okay, so current lag behind voltage by an angle 90 degrees. Here it is an load whose inductive load, that's why voltage is behind voltage value, current is in behind voltage by an angle theta. But in case of pure inductor, its value is going to be 90 degrees. Current lag behind voltage by an angle 90 degrees. That's why. So I have represented, since this is what I have taken as reference. So voltage drop is going to be, so voltage current multiplied with reactance of this. So it is at an angle of 90 degrees. If we assume that like this, voltage in case of inductance, so current lag behind voltage by an angle 90 degrees. So if we assume here it is, so current value is always lagging behind by an angle 90 degrees. So this is voltage drop across reactance. This is voltage drop across resistance. If we join these two, that gives the total voltage drop across this impedance. Okay. So that is it clear? Now, once we get this phasor diagram, we can easily evaluate the regulation of a given transmission. So now, this is voltage drop across impedance. Voltage dropping across impedance plus voltage drop at the receiving end, you will get the total voltage just by applying Kirchhoff's voltage law. So this is voltage drop. This is voltage drop across the impedance, total impedance. This plus this directly gives voltage at the sending end. So it is making some angle with the reference current. So both the currents in this case, that is same. IS is equal to IR. So we can take this angle as this is the phase angle between these. Now the final vector diagram, if we observe, so that is in this fashion. So sending end voltage is equal to receiving end voltage plus drop. Okay, so I think you have noted. So if the loads, so same diagram here, if we observe here, voltage is taken as reference. Voltage across the load is taken as reference. In the previous case, current is taken as reference. Both vector diagrams are same. Okay. So here what I have assumed is 0.7% lagging. So load. So lagging behind, current is always lags behind voltage by an angle 90 degrees in case of lagging loads. Okay. So both the figures are same. But what I have assumed is, in this case, voltage is taken as reference, we at an angle 0. We are at an angle 0. That's why I have represented in this phase. Here the drop is in phase with current. So IR drop is in phase with current. And this is, so this is IX. This is voltage across reactance. So voltage across reactance always it is in 90 degrees with this current. Okay, that's why I have represented in this fashion. If we take here, so angle between these two, voltage drop across the reactance and this current, that is 90 degrees. That's why I have represented, added to this voltage drop. So resistance, terminal voltage or voltage at the receiving end plus voltage across resistance plus voltage across reactance, which gives the supply voltage. Okay, when the load is lagging load. So if it is a purely resistive load, if we consider a purely resistive load, so IR and VR are in phase. So here it is a lagging load, here it is a resistive load. In case of resistive load, voltage IR and VR, the receiving end voltage and current, both are in phase, and this drop, IR drop, is in phase with current. Here it is in phase with current up to this. This is drop, IR drop. Okay, that is in phase with current. So in case of reactance, so reactance voltage drop across reactance Vx. So if we take assume that is always 90 degrees with current. So that's why I have represented same values at this point. So this is voltage drop across reactance. This becomes impedance drop, voltage across impedance Vz. Okay. So voltage across then receiving end plus voltage across impedance directly gives supply voltage. So if the load is resistive load. Similarly, we can implement in case of capacitive load. All the three figures are same. Most of the cases we use only this. The load generally because the loads are lagging loads. Okay. Now this is receiving end voltage. So here the current value. So current value means this is the current value leads voltage by an angle. Here it is leading power factor. So voltage drop across resistance is in phase with IR. Okay. And also the reactance drop is always so 90 degrees. So here it is reactance drop. If we observe voltage across reactance, so again it is making 90 degrees with the current. Okay, that's why I have represented in this fashion. So now again this becomes Vz. Okay, VR plus Vz is equal to Vs in case of capacitive. Okay, are you able to? Can you able to draw these figures? Okay. So once now we have considered only the lagging loads. In the previous what we have seen the diagram taking current as reference. Now we'll try to evaluate the regulation of a given short transmission line. So here from the vector diagram, Vs is equal to Vs cos phi is equal to Vr cos phi r plus IR into R. So are you able to follow? So Vs sin phi s is equal to Vr sin phi r plus IR into X. Note down these two equations. Once you have written, just inform me. Okay, how you will get this? That is, from this if we observe this phasor diagram, so here it is. If we resolve on y-axis, this is y-axis, Vs cos phi s. That is, if we resolve on x-axis, so Vs cos phi s is equal to, okay, Vs cos phi s. This is, so cos of phi s, which is equal to x component is equal to, so Vr into cos phi r. So this vector, if we resolve on the x-axis, Vr into cos phi r plus, so we can directly add this component IR into R. So that gives the entire x component of this Vs vector. That is first equation. So Vs cos phi s is equal to Vr cos phi r plus IR. Okay, is it clear? Similarly, resolve on y-axis. Vs sin phi s is equal to, now this is resolved onto y-axis. So now this is Vs just a minute. Now if we resolve this vector onto y-axis, this is Vs sine phi s, which is equal to, now again same procedure. So resolve this Vr onto y-axis, Vr sine phi r plus, okay. Now here if we resolve onto this, so this term becomes 0. So directly ix into ir. So ir into x, this is ir into x, that is vertical component. Directly you can add to this vertical component. So directly gives these two equations. Is it clear? The same equations I have written. Once you can be able to follow these two equations, so these are the two equations. Okay. So Vs cos phi s is equal to Vr cos phi r plus Ir into r. Vs sin phi s is equal to Vr sin phi r plus Ir into x. Next, just from these two equations, squaring and adding. So just square the two equations. Vs square into cos phi s square. So first equation, if we square on both sides, this becomes a plus b whole square is equal to a square plus b square plus 2ab formula, and add those two. Once we add these two, so sine square plus cos square, sine square phi plus cos square phi s is equal to 1. So you will get phi s. Similarly, here it is also Vr square cos phi r square, Vr square sin phi r square. You will get Vr square, and the rest of the terms if we write and take common. So after simplification, you will get this equation. Vs is equal to, that is sending end voltage is equal to receiving end voltage, and these are the parameters: resistance, reactance, and also the phase angles. Okay, note down. Once you have noted, please inform me. మీ క్లాస్ రిప్రజెంటేటివ్ ఎవరమ్మా?
201 సార్.
201 ఓకే ఓకే. ఇన్ఫార్మ్ చేయండి ఎవరో ఒకళ్ళు, నాకు రాసుకున్నాను సార్ అని చెప్తే నెక్స్ట్ ఫాలో అయిపోవచ్చు. Once you have written, try to solve this one. Squaring and adding. Okay. The next, the same here. So if I observe this terms, I square by IR square by VR square into R square plus X square. Here the values are too small. The resistance values and reactance values in case of a transmission line, that is too small. And if we square that value, so it is almost equal to 0. So it is very much less than 0, very much less than 0. That's why we have eliminated, neglected these two terms. Okay. So I'm writing VR into 1 plus 2 into IR into R cos phi R by VR plus 2 into IR X sin phi R by VR whole to the power of 1 by 2. So just neglecting this term, higher order term. So because its value is going nearly equal to 0, so it is almost 0. So we can neglect that term. And now using binomial expansion, if we write, so for this, and neglecting the higher order terms, so we can limit this to only up to the second term. So you will get Vs is equal to Vr into 1 plus half into the second term. So this power half into the second term, and the higher order terms can be neglected. The last third term and fourth term can be neglected. So finally, its sending end voltage is nearly equal to, so that's why approximately equal to VR plus IR into cos phi R plus IR into X into sin phi R. This is the final equation what we have obtained. The sending end voltage in terms of receiving end voltage. Okay. Here Vs is the sending end voltage corresponds to a particular load current and power factor conditions. Okay. So power factor conditions means it may be a unity power factor or that may be a leading power factor. Here what we have assumed is lagging power factor. That's why you have obtained this values. So that is, we can also consider it as leading power factor and also unity power factor. So then in those two cases, the equations may slightly change. Instead of positive, you will get negative sign, and instead of one term can be sine 0. If the phase angle is 0, sine 0 term can be 0. So cos 0 is 1. In terms of unity power factor, VR plus I into R. Only there is no question of cos and phi terms in case of unity power factor. Okay. అర్థమవుతుందమ్మా? ఒకసారి నాకు రెస్పాన్స్ ఇవ్వండి అందరూ. మీకు ఇది కనుక అర్థమైతే నెక్స్ట్ ఈజీ అవుతాయి. నెక్స్ట్ మనకి నామినల్ టీ, నామినల్ పై అన్నీ కూడా మనం చేయొచ్చు. సో ఫాలో అవ్వగలుగుతాం ఈజీగా. ఇది సింప్లెస్ట్. దీనికి ఎక్స్టెన్షనే మీడియం ట్రాన్స్మిషన్. సో ఇది వచ్చిందంటే 50% నెక్స్ట్ కూడా వచ్చేస్తుంది మీడియం ట్రాన్స్మిషన్. ఓకే, ఫేజర్ డయాగ్రామ్. And from the phasor diagram, V sending end is equal to V receiving end plus this. Okay, next. Now, for the equivalent, from the equivalent circuit of a transmission line, so this is the equivalent circuit of a transmission line. Simply it is represented by a resistance and reactance. So here, so if we observe, what is VR dash? VR dash represents no load conditions. So while calculating regulation mathematically it is represented by no load to full load, change in no load voltage to full load voltage by full load voltage into 100. Okay. So here full load, no load voltage means, so this is VR is terminal voltage. Okay, full load means operating voltage. So that is receiving end voltage. That can be also be assumed as receiving end voltage is VR. That is not going to be changed. That is depends upon the load values. Okay, if it is a rated load, that may be rated values. If it is a little bit more or less, maybe that is termed as terminal voltage or receiving end voltage or load voltage, everything is same. Okay, so here it is from no load to full load, the change in no load to full load. Here the no load voltage when there is no load, that means simply if we assume that is open circuited, when there is no load means simply assume that is open circuited. In case of open circuited, current passing through this is 0. IR value is 0. Okay, so once we know that IR value is 0, there is no drop in this. So whatever may be the voltage at the sending end, that appears across these 2 points. Okay, so that's why I have represented VR dash. That means receiving end voltage under no load conditions, which is equal to supply voltage. or sending end voltage. Okay. Now, just percentage regulation is equal to, this is no load voltage Vs minus receiving end voltage by receiving end voltage into 100. Now we have evaluated this Vs. Okay, we have obtained this expression. So this difference Vs minus Vr. So Vs minus Vr, this numerator, uh, that is IR, just by dividing this VR. So you finally will get, so IR into R by VR cos phi R plus IR x by VR into sin phi R into 100. This is percentage regulation of a short transmission. Expression for percentage regulation of a short transmission line. Simply what I have evaluated or obtained from the phasor diagram, so I've substituted in regulation formula, so I'll get a regulation of a short transmission. So here this term we can also express in per unit values. So this is percentage in terms of percentage, or so if we observe, this is reference voltage drop by reference voltage. So directly we'll get per unit voltage. So VR and IR, VR and Vx are the per unit values of this, per unit values of resistance and reactance of the line. Vx and VR. Okay. Complete అయిపోయిందా? So this is a short transmission line. Okay. For our convenience, if we observe the equivalent circuit of the transmission line, it is having sending end voltage, sending end current, receiving end voltage, receiving end current, and it is similar to, it is nothing but a passive network. So if we observe, so any network having 4 terminals or 2 ports can be represented by using parameters. Okay. The next step is representing using ABCD constants. So ABCD parameters are also termed as transmission line parameters. So in this case, the transmission system is nothing but a transmission line. So here it is also having some sending end current, sending end voltage, receiving end current, receiving end voltage, total 4. So using this, a 4-terminal passive network, the voltage and current on the receiving and sending end are related by the equations. So we have already learned about this in networks. So how to represent a 2-port networks using Z parameters, Y parameters, hybrid parameters, inverse hybrid parameters, and also the transmission parameters. This is also called as chain parameters. General circuit parameters, the other terms, ABCD parameters, general circuit parameters, chain parameters, okay, or simply the other term for this is T parameters. Okay, transmission line parameters, T stands for. So whatever may be the name, the equations are, the governing equations are Vs is equal to A into Vr plus B into IR. We can relate the sending end voltage and sending end current, with receiving end voltage and receiving end current using these 2 equations. So Is is equal to C into Vr plus D into IR. So this is So everything ABCD constants of the network. So any transmission line. So transmission line can be represented either a short transmission line or a medium transmission line or a long transmission line that can also that can be represented by ABCD parameters, ABCD constants. Okay, that's why I'm discussing here. So the same short transmission line can be represented using ABCD parameters, and also we can find out the regulation and efficiency using this constants. Okay, now how to find out A? Simply by open circuiting the receiving end. So IR is equal to 0. So directly you will get A is equal to Vs by Vr. Similarly, open circuiting the receiving end, Is is equal to Is by Vr is equal to C. So where A is equal to Vs by Vr. So if we assume Vr is equal to unit value, so A is equal to Vs at IR is equal to 0. So A is the voltage impressed at the sending end per volt at the receiving end when receiving end is open circuited. So units for this is voltage by voltage, you will get no units, dimensionless quantity A. Okay, this and all. So everybody knows this one. About C is equal to simply C is the current in amperes into the sending end per volt on the open circuited receiving end, and its dimension is admittance. So since current by voltage, so it is admittance value. Voltage by current, that becomes impedance. So current by voltage, so you will get admittance. Units is mho. Okay. So here if we assume the terminal receiving end voltage is unit voltage. So per voltage, okay, per unit voltage. So Is is equal to C. So when the receiving end is open circuit. So these are the names. So B is equal to simply by VR is equal to 0. So VR is equal to 0 means short circuiting the receiving end. So voltage is equal to 0 means it is short circuited. Current is equal to 0 means it is open circuited. So I think everybody knows that this basics. So V is equal to Is by VR. So assuming IR is equal to unit ampere or 1 ampere. So B is equal to Vs under short circuiting the receiving. B is the voltage impressed at the sending end to have 1 ampere at the short circuit receiving end. So because this is short circuited, so current passing through this must be 1 ampere. So IR value must be 1 ampere. So now, so Vs is equal to the voltage impressed at the sending end, Vs. That becomes parameter B. So units for this is voltage by current, you will get ohms. So impedance, dimensions, that is units for this is ohms. This is also called as transfer impedance. So V2 by I1 or I1 by V2. So that is termed as transfer. So here it is called as transfer impedance. So D is equal to, again, similarly D is the current at the sending end for 1 ampere of current at the short circuit receiving end. So here the voltage VR is short circuited. So VR is equal to 0 and current passing through this short circuit path must be unit value. Okay. So here the relation between current at the sending end and current at the receiving end, so gives D. So units for this, again in this case current by current, you will get same dimensionless quantity. This is also, so current by current, you will get a constant value. So this is about ABCD parameters. We can represent either any transmission line using this constants. Now I want to apply the same to our short transmission line. And one more, for a passive network, we have the relation AD minus BC is equal to 1. If it satisfies AD minus BC is equal to 1, that is, the network is said to be a passive network. Transmission network is a passive network. Okay. So transmission system is a passive network. All the elements present in this are passive elements. Passive elements means resistance, inductance, capacitance, are all these are passive elements. Active elements means voltage source, current source, which supplies energy is called active elements. So transmission system. So if we just remove the sending and supply, so that becomes a passive system. So if it satisfies AD minus BC, the system is said to be a passive system. Now the ABCD parameters for a short transmission. Simply, the sending end voltage and the receiving and current can be represented from the network. So if we write the equations, V sending end is equal to V receiving end plus IR into Z. What is Z? Z is total impedance of the transmission line. Okay, R plus JX, that is considered as Z. Magnitude values, Vs is equal to VR plus IR into Z. Okay. Similarly, if we relate the sending end current and receiving end current, since these two are, everything is connected in series, so sending end current is equal to receiving end current. So if we compare these two equations with standard equations, simply you will get A is equal to 1, B is equal to Z, C is equal to 0, and D is equal to, okay. So if we compare with standard equations, that is Vs is equal to A into VR plus B into IR. Similarly, Is is equal to C into VR plus D into IR. So standard equations. So if we compare those two, you will get A is equal to 1, B is equal to Z, C is equal to 0, D is equal to 1. And if we verify for a short transmission line, AD minus BC is equal to 1. So A in value and D value is 1 minus Z into 1, which is equal to 1. So that means the short transmission line is a passive network. So are you able to follow? కొంచెం ఫాస్ట్ గానే ఉంటుందమ్మా, సిలబస్ మనకి ఫాస్ట్ గానే అవ్వాలి. ఓకే, నోట్ చేసుకున్నారా? Is there any doubts? Is there any doubts up to this? Okay, we'll continue in the next session. I think tomorrow's class you can continue. So note down these equations. If you have textbooks, there is no problem. You can again you can solve the examples. Otherwise, you can follow. You can follow any textbook. So everywhere it is present. Okay, otherwise, note down a little bit fast. Okay. So any doubts regarding today's class? If you have any doubts, immediately you can bring to my notice so that we can discuss. Now the time is almost 9:55. Thank you.